So let us welcome the next lecture of real analysis 2. So in previous lecture, so we have started chapter 3, that is completeness, connectedness, compactness, and totally boundedness. So just revise what we have seen in previous lecture. See, yeah. So this chapter number 3. So 3.1, it is more about open sets. 3.2, that is connected sets. 3.3, that is bounded sets and totally bounded sets. And 3.4, it is complete matrix spaces. So up to 3.3, so we have seen in previous lecture. So up till 3.3. So 3.4 will define complete matrix space, and there are certain properties on complete matrix spaces. So in this lecture, so see, so in previous lecture, first we define open ball in subset of matrix space. So what is the difference between open ball PA and open ball PM? So it is open ball in subset A and it is open ball in matrix space and there is a relation between open ball in subset and open ball in matrix space. So already we have seen it. Then we define connected set in matrix space. So after that, we have seen definition of bounded sets and totally bounded sets. So in that, we have seen diameter of set. What is diameter of set A? So it is it is longest distance between any two points. So diameter of A, which is defined by least upper bound of rho x y, where x and y are elements of A. So that part which we have seen in previous lecture. So let us continue. So next topic, that is complete matrix spaces. So what is the definition of complete matrix space? So first we define complete matrix space. See, so capital M be a matrix space. Then when we say M is a complete matrix space, if every Cauchy sequence of points in M should converge to point in M. So capital M is a complete matrix space if, see, so when we say capital M is complete matrix space, every Cauchy sequence of points in M should converge to point of M. Means it should converge to inside of M. So then capital M will be complete matrix space. So this is the definition of complete matrix space. So note that. So L square, that is square, it is a space of square summable sequences and which is a complete matrix space. So again there is another theorem, that is if M rho is a complete matrix space and there is a closed subset of M, then A rho is also complete. Yeah. So when we say A rho is complete, if A is closed, then it is sufficient. So original matrix space should be complete matrix space. So it is a required condition. So if original matrix space is complete and A is a closed subset of M, then naturally A rho also complete matrix space. So next theorem. So let M rho be a complete matrix space, and for each n belongs to M, let Fn be closed bounded subset of M such that, see, so it is a family of subsets, closed bounded subsets of M which satisfy this condition. That is, F1 is the largest, F2 is containing F1. So naturally F3 is containing F2 and F2 is containing F1. So it implies F3 is also containing F1. And likewise, so Fn plus 1 is containing Fn, or Fn contains Fn plus 1, and likewise. So that is first condition. And diameter of Fn tends to 0 as n tends to infinity. So if this situation is there, then what is the intersection of this family? So family of closed bounded sets. So their intersection should contains precisely one point. So geometrically you can observe, see, just a minute. Suppose, so it is F1, so you can take it as F1. So F1, it is the largest set, so F1 contains F2. So again you can draw F2, so which is subset of, see, so this F2, so F2 is contained in F1. So next F3 is contained in F2, so you can draw, yeah, just a minute. Yes, yes. So F2 contains F3, and likewise. So this process continues. So this is family of closed bounded subsets of M. And what is the diameter of Fn? So as n tends to infinity, means as n approaches to infinity, so this set approaches to singleton, and this singleton will be in each closed bounded subset of M. F1, F2, F2, it goes to infinity. So precisely this intersection contains one point. So this is statement of this theorem. So next, there is a definition of contraction mapping. So what is contraction mapping? So definition of contraction mapping. Yeah. So let's suppose M rho be a metric space, and T is a mapping from capital M to M. So we say that T is a contraction on M if there exists alpha. So alpha is a real number. Basically, it is positive real number. It satisfies the conditions alpha strictly less than 1 and greater than equal to 0. So it may be, yeah. So what is contraction mapping? So let M rho be a metric space if it is a mapping from capital M to M. So we say that it is a contraction on M if there exists a real number alpha. So it satisfies this condition alpha is less than 1 and greater than equal to 0, such that says that, so rho of tx ty, so what is tx? But it's t of x and ty, that is t of y. So distance between tx and ty should be less than equal to alpha times distance between x and y. It should be true for all x y belongs to M. So this is the contraction mapping. Means T is a mapping from capital M to M. M is a metric space. So when we say T is a contraction mapping, so there should exist positive real number alpha, and it should satisfy this condition. So alpha should be a real number, and it should lie between 0 and 1. It may be 0, but surely it's strictly less than 1. So it satisfies this condition. Rho of txt1 should be less than equal to alpha times rho of tx x1, and it is true for all x5 belongs to M. Means if we operate T on M, then what will be its image or what will be its range? So that T contracts that matrix space M. So this is the property of this mapping, means it is contraction mapping. So next, so here this number alpha should be independent of xy, means it is true for all xy. So this alpha should satisfy this property for all xy belongs to M, means alpha is independent of xy. So next theorem, that is Picard's fixed point theorem. So this is the most important theorem of this course. So I will prove this theorem. So first, what is statement of this theorem? See. So statement of this theorem. So let M rho be a complete metric space. So M should be complete metric space, and T is a contraction mapping on yum. So then there is one and only one point x in yum such that Tx equal to x. So this point is called fixed point. So if yum is a complete metric space and T is a contraction mapping on yum, so then there should exist at least there should exist only one fixed point for this contraction mapping T, that is Tx equal to x, and it is true for only x, and x is unique point in that set metric space yum. So this is often stated as T has precisely one fixed point. So we'll prove this theorem. So what we have given and what we have to prove. So first let us see. So we have given that yum is a complete metric space and T is contraction mapping on yum, and we have to prove this. Yeah. So there exists unique fixed point for this T in yum. So for that, suppose so let's take 2 points xy from yum, and we have, so what is T? So T is a mapping from, so we'll change color. Yeah. So let's take, suppose T is a mapping from capital yum to yum. So since T is a contraction mapping, so it will satisfy the condition that is rho of Tx Ty should be less than equal to alpha times rho of xy for some alpha, and here alpha strictly lies between 0 and 1. It may be 0 or strictly greater than 0, but surely strictly less than 1. So alpha is a real number and it satisfies this condition. So this is just because of uh, T is a contraction mapping. So you can give reason for this. Since T is contraction mapping, so we are just using definition of contraction mapping. So next again, so repeatedly we are using T is a contraction mapping. So next time, what will be rho of T square x, T square 1. It will be again alpha times rho of Tx Ty, but rho of Tx Ty, it is already less than equal to alpha times rho of xy. So here we are putting bigger value, so it will directly use us rho of T square x, T square y will be less than equal to alpha square rho of xy. So indeed, for any n belongs to set of natural numbers, it is easy to show that. So this statement, that is rho of T raised to n x, T raised to n y. So naturally, what is T square x? So T square x will be T of Tx. So we are operating T on x two times. So what is T raised to n x? So we are operating T on x n times. So rho of T raised to n x and T raised to n y will be less than equal to alpha raised to n rho of xy for all xy belongs to m. So you can write this equation as was equation number 1. So now choose any fixed point x0 from yum. Yum is a complete metric space. So here we are considering one sequence. We are making, or we are developing one sequence. So let's take x1, which is the image of x0 under T. So x1 we are taking tx0, x2 we are taking tx1, but x1 is equal to tx0. So naturally it will be t square x0, and we will continue this process. So you'll get xn plus 1 equal to txn, and that is t raised to n plus 1 x0. And likewise, so we developed one sequence, that is sequence x raised to xn, and first next we'll prove. So the sequence is Cauchy sequence. So for if m and n are two natural numbers with m strictly greater than n, say that suppose m strictly greater than n by suppose p. So we can write m as n plus p. So we have, see, so what is rho of x and xm? So here we are putting value of m, that is n plus p. So naturally that is rho of x and xm plus p. So here we are using triangle inequality. So it is less than equal to rho of xn. So we are adding here xn plus 1, xn plus up to xn plus p minus 1, means we are adding here p points between xn and xn plus p. So from that we'll get, see, so rho of xn plus 1. So here I'm putting value of xn and xn plus 1. So it is t raised to n x0 and xn plus 1, that is t raised to n xn. So likewise, so value of xn plus 1 and xn plus 2, and similarly value of xn plus p minus 1 and xn plus p. So we'll get this inequality. So this by 1. So we have, what is t raised to n x0? So t raised to n x0, which is less than equal to alpha raised to n t alpha raised to n rho of x0 x1. Similarly, here it is less than equal to alpha raised to n plus 1 rho x0 x1, and likewise. So we get this equation, that is rho of xn xn plus xm less than equal to alpha raised to n into rho x0 x1 plus alpha raised to n plus 1 rho x0 x1 plus up to plus alpha raised to n plus p minus 1 rho x0 x1. So here you can take this alpha raised to n rho x0 x1 common from each term. So in bracket it will be 1 plus alpha square plus up to plus, and it goes to, actually it goes to alpha raised to p minus 1, but still, yeah, so plus I can write alpha raised to p minus 1, and which is again less than equal to, so alpha raised to n. I'm considering here infinite number of points, so instead of finite number of terms, so if I add infinite number of terms, so this side will be greater than, so you can write alpha raised to n rho of x0 x1. So in the bracket it will be 1 plus alpha raised to alpha square, and goes to infinity. So you can replace addition of finite terms by addition of infinite terms. So resulting side will be greater than equal to, so you can write this inequality. So here using, yeah, it is geometric series. Since alpha, see, alpha is strictly less than 1 and greater than equal to 0, and so this bracket, that is summation of alpha raised to n varies from 1 to infinity, will be geometric series, and using convergence of geometric series, so value of this summation will be 1 upon 1 minus alpha. So it will gives rho of xn xm is less than equal to alpha raised to n rho x0 x1 divided by 1 minus alpha. So since here alpha is strictly less than 1 greater than equal to 0, so therefore what is the limit of alpha raised to n? So naturally it will be 0 as n tends to infinity. So it follows that, see, as n tends to infinity, so the sequence alpha raised to n tends to 0. So naturally, what is rho x and xm? So as n tends to infinity, so rho x and xm, so naturally it tends to 0. So can be made arbitrarily small by taking m, and hence m also, because so we write m as n plus p, so sufficiently large, but for a sufficiently large value of n, so this rho x and xm tends to 0, means it we can make it arbitrarily small. So this sequence xn is a Cauchy sequence. So by hypothesis, so already it is given that m is a complete metric space. So this sequence xn is a Cauchy sequence, m is complete metric space. So naturally the sequence should converge to point of m. Suppose that point is x. So already we have proved xn is a Cauchy sequence. It is given that m is a complete metric space. So naturally the sequence should converge to a point of m, and suppose that point is x. So therefore limit of xn as n tends to infinity should be x. So also it is given that, so T is a contraction mapping. So this is property of, already it is property of contraction mapping. So it is that, see, contraction mapping is always continuous mapping. So contraction mapping is always continuous. So using this property, so naturally T is contraction, therefore it is continuous, and it is continuous on m. M is complete metric space. So naturally, if a limit xn is x, so what will be limit of txn? So naturally it will be tx. So this is property of continuous function. So it is property of continuous function. So it will gives us sequence xn converges to x and sequence txn also converges to tx. But what is tx? So next we'll prove this tx and x is equal. So next, see, but what is txn? So txn is xn plus 1. So naturally xn plus 1, and so what is xn plus 1? Xn plus 1 is txn. So naturally txn means xn plus 1. So it will be subsequence of sequence xn, because how many terms are there? So what is sequence xn plus 1? So you can observe what is xn plus 1? N varies from 1 to infinity. So this sequence start from, so for n equal to 1, so it is x2, x3, x4, it goes to infinity. And what is sequence xn? So sequence xn n varies from 1 to infinity. So the sequence start from x1. So for n equal to 1, so you are getting x1, then x2, and it goes to infinity. So naturally xn plus 1 will be subsequence of sequence xn, but already sequence xn converges to x. So therefore sequence xn plus 1 also converges to x, being subsequence of sequence xn. So both sequences xn plus 1 and xn converges to same limit, but already this sequence converges to x, and therefore this sequence converges should converge to also x. But what is this sequence? This sequence is txn. So txn converges to x and xn converges to x. But already txn converges to tx. So already we have written limit of txn is tx, and here what we are getting? So we are getting here txn also converges to x. So therefore this tx and x should be same, and hence it gives that x is the fixed point of this contraction mapping T. So next we'll prove. So this fixed point, it is unique fixed point, means there is only one fixed point for contraction mapping in complete metric space. So for that uniqueness, suppose y is another fixed point and y is different from x, and it is another fixed point, so y cannot be a fixed point. So that we will prove. So for suppose on the contrary, if y is another fixed point, then what happens? So it will satisfy a definition of fixed point. Already what we have, tx equal to x, because x is already one fixed point and y is another fixed point. So we are getting ty equal to y and tx equal to x. So here I'm using definition of contraction mapping, that is rho of, yeah. So here rho of xy will be equal to rho of tx ty, because x equal to tx, and see y is equal to ty, and rho of tx ty less than equal to alpha times rho of xy. So what we are getting here? So rho of xy is less than equal to alpha times rho of xy. So rho of xy is not equal to 0 because x is not equal to 1. Since x is not equal to y implies that rho of xy is not equal to 0. So you can divide both sides of this inequality by rho of xy, and from that you will get, so alpha greater than equal to 1. So this contradiction. Since rho xy not equal to 0, this implies that alpha greater than equal to 1, which is contradiction to alpha less than 1 greater than equal to 0. And we got this contradiction because we assume that, so y is another fixed point, that is ty equal to y, so which is not true. So therefore ty not equal to y. It means that there is only one fixed point. So I'm giving here some homework, so you should do this homework at home, compulsory. So first question, prove that Rd is complete metric space. Second, ask where is complete metric space, and here let us consider one mapping tx equal to x square. So here x greater than equal to 0, less than equal to half, 1 by 3. Question is that prove that T is contraction mapping on this closed interval 0 to 1 by 3. So do this. Yeah. So I will stop here. So in next lecture, I will continue the next topic, that is compact metric space.